So I'm pleased to introduce Peter Corcoran.
Corcoran.
Thank you, Peter. He is a professor at the, let me get it right, the National University of Ireland, Galway. So he's a professor, and they've partnered with Xperi on some projects, and he's going to talk with us about hybrid, semi-parallel deep neural networks, and go through some methodologies and use cases for that. So thank you, Peter.
Okay, so just to open the talk maybe and set a context, I was at the enabling sessions, enabling technologies session earlier, and I asked a couple of hardware manufacturers who are making hardware for these networks if they could support parallel CNNs. Okay, if I might want more than one CNN to run at the same time. And I got the kind of answer I expected was, oh, we're working on that. Okay. This is interesting. It's kind of something we discovered accidentally. And it's a way to put parallel networks together into a conventional single input and output network. And I'm going to rattle through it a little bit. This is my sort of keep me in sync slide. So this will appear a few times. And I'm going to start with just a few quick kind of things. I'm going to use some pictures here, fully connected networks, pooling kind of network layers, and convolutional layers. These are kind of typical things we use to describe neural networks. The other point I'll make about neural networks is that there's been a rapid evolution in the last handful of years, and even in the last 2 or 3 years, there have been enormous steps forward. One of the points I had a discussion with my PhDs is that the philosophy now is we make things deeper and deeper, right? If we can't get the network to work, let's just add a few more layers and train it a bit more, and it'll work eventually, right? So the underlying philosophy is make things deeper and deeper. This approach is a little bit different, okay? So every story has a beginning, and the start of this story was when my PhD was about 2.5 years ago, was doing some initial work with deep learning networks, and he did some work on facial expression analysis, okay? To set the background for that, we're just going to talk a little bit about the data training issue. So typically, as academic researchers, we've got a particular data set that we've gathered somewhere, or we've put together a number of data sets, or there are industry standard, quite large data sets, and more and more of them are appearing. So we do a bit of training, right, and we get some results. And as I said, we make the network deeper and deeper. Eventually, we get a nice set of results. But of course, it works very well on the data that we fed into it. And then you get someone else does another set of experiments with a different set of data, or possibly even the same data, but with certain tuning or modifications. And they get a different set of outputs. And the question now is, what happens when you try to put the data from one into a different sort of network, okay? And of course, what tends to happen is you don't really get very good outputs. You don't really get the results you expected. And that's something, if we're publishing an academic paper, we're always asked to compare it with everybody else's results and things, and we have to make ours look better. So we tend to fall into this trap. So here's the question: could we actually take some of these works that are in the literature and build something, a hybrid, a little bit of a, well, this is my PhD has seen too many of my presentations, so this is his representation of it. And the answer is we can actually do that. So the early work on this was based around 3 main data sets: RAFD, CK+, and both of these data sets, they're on the resource slides. They're fairly well-known networks. They're not that huge of a data set. They're, you know, tens of thousands of images, but this was a kind of initial work, proof of concept, okay? And another image, this is the Japanese female face database, and this one is apparently quite challenging. So there wasn't enough here to train a network on it, but it was used as a test kind of reference, okay? And both of these main data sets, the RAFD and the CK network, both of them had networks trained around them. So my student did some testing with these networks, and he got everything to work. Okay, and then he thought, well, these two networks are reasonably, there's certain similarities between these layers. Okay, and I'm not going to go into the details here, but if you want to go back and recreate it. So he said, well, I could actually build a network that combines the two, and he did this intuitively without thinking of any process behind it. So I'm going to explain the process to you in a minute. But he got this particular network here. So again, just to give you an idea, and what he did was he trained that network on all of the data, right? At least on the training portions of the data, because he had to keep some for testing, obviously. So what he found out was quite interesting. When he trained his combined network, right, the RAFD data, right, his combined network performed better, and pretty significantly better than the RAFD, right? He found it also performed better. 19% here, 16%. It performed better on CK+, not quite as impressively better, but better. And then finally, it also performed much better. Both of these two databases, networks, when applied to Jaffe, were pretty bad. I mean, they had 50, 70% error rates. His combined network came out at 13%. So this was really a proof of concept paper, but he suddenly realized that the results were better than he expected. And there's a paper at the bottom here if you want to read a little bit about that initial work, okay? So the key takeaway here is that this new network, which was built from the two original networks, had a better result once it was trained than the individuals. Now, he originally thought it would be like a vote taker, and he'd get, if things worked out well, he'd get the same performance on each network, or each original set of data, as the individual networks. So this led to the development of what we call the hybrid semi-parallel deep networks. And we then, the idea was that there are lots of data sets or networks in the literature built around specific data sets. Can we take advantage of the different research that's been done in the literature and combine these networks together to get a smaller network, right, but a network that can learn what the original networks do, okay? And this merged network, we call the SPDNN, or the semi-parallel network concept. Now, we actually figured out, okay, the first few times we did this, it was done almost haphazardly, look, oh, there's a few things, let's try this approach, and it worked. But then we realized it was actually a form of graph contraction we were doing. And the PhDs produced this workflow which steps you through the process. But I'm actually going to do a worked example because this doesn't really make sense. It's much easier if we look at a very simple example. So here we have three very simple networks. These are actually used for a problem in iris segmentation, taking out the iris from an eye region, because in order to do accurate iris recognition, it's important to get out the iris. I'll say a little bit about that later, but these are very simple networks that were used initially. And you see here, I've got two networks. This one has two convolutional layers and a fully connected layer. This one has three convolutional layers. This one has three convolutional, one fully connected layer, okay? The key point with this is we've got 10 hidden layers here in each of these networks. If we were to run each of these in parallel, we'd have to solve those 10 layers, and I'm drawing them in a kind of graph format here. So here's my 3x3 convolutional layer, and it's at step 1, at step 2, and at step 3. This is the 4x4 fully connected layer. And each of those is represented in that format. Now, it's much easier if we add a little bit of color in. So if we look at, this is the first network, second network, the third network. 3 hidden layers, 3 hidden layers, 4 hidden layers, okay? The point here, this is a 3x3 layer, this is a 3x3 layer, this is a 7x7, this is a 7x7, okay? We can actually join these two together, so that becomes this node here. We can join these two together, that becomes this node here, okay? And we get an initially reduced network. So you can see that's a little bit smaller. It's not a huge amount smaller, but we've got rid of a couple of those layers. Now, the trick bit is we now go to the output and we can work backwards. And we see we have 4x4 fully connected layers here. Here we have a 7 and a 7 by 7, two convolutional layers. And so these two can be merged together like this, and these two can be merged together like this. So now we've got 1, 2, 3, 4, 5 hidden layers instead of 10. So we got rid of 50% of the network layers. But what's interesting, we now have one input, one output. And this network, it has the characteristics of the three networks, the three separate networks that we had. Okay? And if we go back to drawing it in these block forms with the convolutional layers and the fully connected layer, you get something like this. Okay? So this is half the size of this. Okay. Now, we, of course, went and did this on more complicated networks. So I'll just give you a couple of case studies to show you some of the results. And Jeff was keen as well to kind of give some actual comparisons and things. I'll just start with recapping on the idea that we're trying to replace multiple parallel networks, right? Now, we could have chosen to have these three networks, just run them directly as they are, and then we'd have to add something at the end here to combine the outputs. Okay, this would be a more traditional approach, so we'd add something like maybe an SVM or some other type of artificial intelligence to take the three outputs and put them into a single. Or if we do it the SPDNN way, we just simply have a single network, which is built from the original networks. We can say it's always smaller in size than the total of the individual networks. It does not require any additional machine learning. The actual output is built on into the refined network. And the results we found in quite a few cases now, so I'm just going to talk about two here, but in quite a few cases we found modest to impressive improvements in the actual performance from a smaller network. Okay. We'll also mention that not every time, this won't always converge. So when you're training it, sometimes it doesn't work. And sometimes it takes a while tweaking things to get it to work. So let's take a first case study is iris segmentation. So I mentioned this already. It's important to get the iris very accurate. And some of the problems we're looking at with Xperi are about doing this on mobile devices, where the iris size is much smaller, the device doesn't stay still, it moves a bit. I talked a little bit about this in a different context in another talk. But just to give you some practical, these are the kind of artifacts you get. You're trying to find a ground truth of the actual iris in this image, but one particular type of network will give little artifacts like this, another one will give different artifacts. We'd like to get this result here, so we need to combine these networks to give us our ideal result. So we've published a paper based around this set of iris approaches. This uses different size 9 by 9 kernels going into a 7 by 7 is the base one here. Then a larger 11 by 11 going into a 9 by 9. 13 by 13 going into an 11 by 11. So you can see there's a kind of using larger kernels here and then scaling them back down again. Okay, this was our first approach at this problem and our first, I would say, successful approach, and it was quite effective. So to give you some context, this is using pixel level segmentation. So we're talking about every pixel counts towards the accuracy. And we compared this with a large number of state-of-the-art methods for iris segmentation. Excuse me. So you can see here, Ubris is a large, high-quality iris database, right? So they're very nice, big, in a sense, you could say it's an easy database, okay? Mobio is one taken on mobile devices, and it's a very difficult data set because the images are bad, they're blurred, there are various issues with them. So these methods here, in fact, won't even work on Mobio. These ones down here are giving results which are pretty unimpressive. 50% is about the best. Our approach gets 97% on this very challenging database, and it gets better than any of the state-of-the-art in the Ubris database. Now, the technique has been refined, but this is published in a paper, so you can read a little bit about it, okay? And Jeff then wanted me to kind of show you how this is improved. So here are the 4 nets we've combined, and you can see the number of nodes or interconnections. You can see in the largest one with fully connected layers, this is almost 1 million connections, which is quite large. If you added all these together, you were going to implement them in parallel, you're talking about 1.6 million interconnects, as it were, which is pretty big network. If you use our technique, you reduce that to just over 1 million. Okay, so we could say it's a 33% reduction. And again, remember, we're better than people. Now, actually, we've built a much smaller network, but I can't tell you about that. Okay, so this is the first go, but you can see here immediately, just applying this, there's an immediate benefit. The other interesting problem that I'll talk about today was in automotive street scenes. And this is kind of interesting as well, because we did this work about 2 years ago, and we're still trying to get the paper published. Okay, so like many groups now, we don't bother too much about where we're going to publish papers anymore. We just put everything on archive, but we didn't know about it at the time. And in fact, the latest journal we submitted this to, they said we should compare this with state-of-the-art methods, which is kind of ironic, because when we originally did the work, there were no state-of-the-art methods. What we're doing is we're actually developing mono imaging, right? Mono sort of depth. So from a single image, we're training a deep network to give the same results as a stereo depth estimation, okay? And we're using the Kitty stereo data sets. There's a 2012 and a 2015 version, because these have quite a lot of image automotive street scenes, okay? And again, I just mentioned some of this relates to the original work, but we've updated, the paper has been updated on archive and has been compared. Really, what we're interested in here is the networks that are combined together. So this is a much more complicated network, where 4 fully convolutional networks are combined together. Now, Jeff was complaining, I think we can actually read those numbers, but again, I don't expect you to understand. I just expect you to see this is a single size of kernel. Here we zoom in a bit and then we go back out again, and you can see there are some variations between these 4 convolutional networks. So what my PhD students told me was none of these networks would converge on their own, but when they put them all together in the SPDNN, they were able to get them to converge. There's also 4 fully connected layers, networks 5 to 8, which have a fully connected set. So these are much larger because of the fully connected parts, okay? And this is my diagram explaining how these were put together with SPDNN, okay? So again, just ignore a little bit some of the fine detail. So networks 1, 2, 4, and where did network 3 go to? That should be probably 3. So these guys, if you go through here, this convolution part, this network here is a complete convolution path. Okay, so networks 1 to 4 have the same convolutional output here. Networks 5 to 8 are the fully connected networks, and these bits here are the first few stages of each of the networks. So you can see this network here going down through here gives me one of the networks 5 to 8. And this path here, up through here, gives me one of networks 1 to 4. So all of this can be implemented as a single deep network, okay? So again, comparing these, if you look at the individual networks, the convolutional ones are relatively small, a couple of thousand nodes. When we get to the fully connected ones, these have 20-odd thousand each. Total number is 92,000 interconnects. The merged network is about a quarter of the size, a little bit more than a quarter, let's say, 30% of the size. So we've achieved a significant reduction in the size of network, but none of these individually could be could be got to converge. And then we built a number of different models. I think model 3 is the most effective. And this is the stereo. We use the stereo as a ground truth because you need sophisticated LiDAR to get, and there wasn't a reference ground truth with Kitty. But this has shown very promising results. And as I say, it's been updated now and compared with other methods that were developed after this was originally proposed and put out there. Well, actually, it wasn't on archive. Sorry, we weren't putting things in archive at that time. Just a few more examples there. So, and I'm spot on time. That's amazing. It's amazing. 4 seconds after. Come on. Questions?
Good afternoon. My name is Ed Royce, and I'm with Socionext. So those last two results, the ground truth versus all the various networks, do you have results that, rather than just showing the actual depth heat maps, do you have results that show the difference or the error between each of the models and the ground truth example?
Not on this presentation, but we can go and ask PhDs that question.
Okay.
I'm sure they can generate. I mean, I think knowing what we know now, this project might be due for another stage of iteration. Because
you calculate those errors, and then you go ahead and you do the sum up all the errors, the RMSE of each of these models. Then you get a relative index that's a single number between each model and the ground truth. Then, right?
There's a lot of numbers in the paper, so I would say look at the resource slides and take a look at the updated paper on archive, because that's only happened in the last few weeks.
Okay.
You know.
Cool.
So and that's what's gone back in as an answer to reviewers.
I mean, these are pretty pictures, of course. But...
Yeah.
Okay,
yeah. Well, I mean, we did try at one point, as I mentioned back here, we were kind of using the stereo depth as a fake ground truth.
Right.
It's not a real ground truth.
Right.
And we did look at buying some LiDAR systems, and I know there's another company just north of Galway, about 20 miles north, that has loads of LiDAR data. But they ain't willing to share it, you see. So
I see, okay. So you're going to shame them, huh?
We'd love to have ground truth data, because if we could retrain this with the ground truth data.
Sure.
And
you use that for your back propagation model and all that.
I'm open to working with someone on that. So.
Cool. Thank you.
Hello, my name is Louis Goncalves. I'm from Datalogic, and just wanted to understand a little bit more detail of how the combining works. And could you go back to the slide which was the faces?
Faces? The very early stage,
yeah, the very first example.
Well, I think that's probably this is this one, I think. Yeah.
Okay, yeah, that's right, that one. So let's see. So
so we've got two 3x3 layers, right? So they can be combined together, right? So we've just got one instead of having two of these, right? We've just got one of them now. Right?
Okay.
So this now goes to node F here, and it goes to node C here. Okay. And so these two C's are together. So we go through here B to C.
Yeah, but so you have two A's and they take the same input, so that's okay. So now those two A's will feed to different things. Well, before they're feeding something separately, now they'll both feed to the same thing. So basically, you're just where you had two A's which were the same size, but they were different weights. Now you use the same weights twice.
One of them went to A and then to C.
Yeah.
The other one went to A and then to F.
Right.
This one goes from here to A.
Yeah.
To F.
Right.
This one goes from here to A to C.
So in the case of A, so my question is, in the case of this A node, which you have two, which are the same size, they have the same input to start, but they go to different outputs, and so you gain because you're basically using the same weights twice, right?
These two networks had the same processing, so we just process once instead of twice.
They had the same similar size of a layer. The weights might have been different in the independent networks.
We retrain this combined network.
Right,
exactly. That's the trick.
Exactly. So the trick is that you have something that's the same size, and so instead of having independent weights, you use the same weights twice, right? And you gain because you can use the same output from A twice, and so you only have to have one A instead of two A's. But then there's another case here, I think, where they go to you combine two, but they go to different outputs. Or actually, let's see.
Well, I think if you trace through it, you'll find
here it's the C. It's the C.
Yeah.
The C that's been
The C
combined,
one here?
right?
Okay.
Yeah. So that C before
C goes to D. It goes
no.
to E.
But
Yeah.
they had different inputs. So before the C, that C got an input from A, and the other C got an input from B, and now you have a C which gets an input from A and from B. So this C is basically twice as big in terms of channels as the original Cs. So you don't gain anything in that case because you have separate different inputs coming into it.
Possibly.
Okay.
If you want, I can hook you up with my PhDs.
Sure.
There's a couple of guys who'd be very happy to get into
Okay.
many detailed discussions about it.
Okay. Sure. Because it seems like in some cases you gain because you can avoid replication, but in other cases you can't because you actually have more channels that you have to keep in.
Well, I know that we've got about 5 or 6 PhDs now using variants of this in other problems that I haven't even discussed. It seems to work quite well.
Sure. Okay. Okay. And if I could, just one other question.
Okay.
With the original faces data, which is a couple of slides before.
Yeah.
So you showed how when you combine them, you get better results.
This one?
Yes.
Yeah.
And
so,
I guess...
so we need to look along the diagonal. This is the CK. This is
CK
the CK network on CK data.
Right.
This is the combined network on CK data.
Right.
Not as big a deal. This is kind of more impressive.
Right. Okay.
But this was the kicker. This is what got us interested because neither of the other networks worked well on Jaffe, but this combined network worked. And we didn't train on Jaffe. That was just kept for testing.
Right.
So that's where we got interested.
Right. But maybe there are other ways to combine also. Like I know that, a common technique people use is you just train a whole bunch of them and then average the result. And that actually gives you a lot better results than each one individually. So maybe a kind of straw man comparison would be just to average those results and see if it's better than...
But then you'd be in this kind of case, this one here, and you wouldn't... If you look at the numbers, then you'd have a much... you'd have to run each of these and then average them.
Sure.
So the point here is we get a smaller network.
Sure.
And in most cases, it gives noticeable improvements on, even though the data sets are heterogeneous.
But maybe there's a compromise between how much you compress and how much accuracy you gain, and maybe if some other way of combining them gives you more accuracy, even though not as much compression and weights.
Okay. Well, we're happy with the graph contraction because there's a theoretical basis.
Sure.
Sure.
Yeah, it's nice.
And again, a different PhD explained it to the first PhD, so that was kind of interesting,
Sure.
Oh, I know what you're doing. The first guy, I don't know what I'm doing, but it works. And then the other guy says, I know what you're doing.
All right, thank you.
So we thought it was worthwhile sharing with people,
Sure, thank you.
Okay. Maybe I'll just go back to that slide.
Hi, I'm Ravi from Qualcomm.
Okay.
If you go to the previous slide, I had a question kind of along the lines. So the two A nodes, they're both 3x3 convolution layers, but if there are differing number of filters, do you concatenate them or do you just merge them if they're the same size?
Okay, so I'll plead the lack of PhD to that one.
Okay, then the other question is, do you fine-tune the weights of this contracted network or do you retrain from scratch?
You retrain on the combined data. So
from scratch?
Yeah.
Okay, all right.
Yeah.
Thank you.
Yeah.
Hi, Jason Nichols from Walmart. So a question for you regarding the input A's and the resultant A. Did you guys analyze the relationship between the weights for the two input convolutional layers and then the resultant weights for the output? Is there some correlation there? Are they averaged? When you retrain, you can see those weights. Did you see any pattern there?
I don't believe we got to that level of trying to understand what's going on here.
Just because if you use some of the common techniques like freezing layers and whatnot, you could potentially train it much more quickly. If you knew a priori that the weights of A should be the average of the two input A's. You could have frozen that layer.
I suppose my PhDs have these big workstations stuffed with GPUs, so they're always complaining things don't train fast enough, but they're
the life of a practitioner. Nothing trains fast enough.
So yeah, I mean, we didn't really. This is one of these things that we haven't got to the point that we got to feel we should understand it better at this stage. We found it works, so we're happy with it in most cases. Maybe the next round of PhDs will say, well, we need to understand why this works. But at the
Thank you.
moment, that's where it's at. Okay.
Go ahead.
Advantage of being the last speaker.
My name is Kamal. I'm from Karl Storz Endoscopy. I was wondering how you choose the component networks, because you mentioned that none of them converged when you train them individually.
Oh, for the automotive. Well,
Yeah.
I mean, we have in other problems, we have used networks that worked. Excuse me, but this monovision problem. So the PhD who's a co-author on this, right? He's kind of been playing around with networks for the last 2 years, and so he kind of conceived of these. Now he has probably a reason why he used these 8 types of networks, right? You can see there are variations. I mean, this one is a max pool 4x4 of 8x8. He could probably, go through individually each of the choices and why he made those particular selections. I'm sort of, unfortunately, it was enough to extract some of the the simplified details here. So I couldn't tell you exactly why these different choices. I mean, here we have kind of 3 3x3 layers, and here we have a different structure with 3 3x3s, and it goes into something else. There is some thinking behind this, but unfortunately, I don't know enough to speak to it.
That's okay. Yeah.
And I just, I'd only be leading you astray. But I'd be happy again, if you'd like to have more information, I'd be happy to introduce you to the PhD, and have a chat with them about it. Okay.
Thank you.
Awesome. Thank you, Peter.
Okay.
Sorry, I had one question. So you mentioned, my name is Kedar, I'm from FLIR. You mentioned the SPDNNs did not train properly. So you had to kind of change the hyperparameters or change the datasets, or?
Well, I think what I was saying was that individually, none of these 8 networks would converge on their
when
own.
you had the SPDNNs, so when you actually combined them, you mentioned sometimes they don't converge at all, right? So did you change the hyperparameters, or did you change the datasets, or what were you kind of doing differently?
Well, okay, so these networks sometimes need to be tuned. The learning rates, the different, as you say,
So
hyperparameters and things. I'm not in the depth of that. That's what the PhDs are doing. I know, for example, not on this, but on the previous presentation, I showed some systems or networks that took months. The GANs, the generative adversarial networks. Now, these things were less of a problem. I mean, we're talking about a few weeks to get some of these things working. But generative adversarial networks could take months sometimes to get working. But now he's got them working. He's pushed out about 3 papers in the last 3 months. So
Thank you.
that's what happens with PhD students. Hey, it's working. Now I can do this, this, and this. And I got to read them all.
Sounds like you have a surfeit of PhD students in Galway.
Well, they're going to be leaving soon. A few of them, so I'll get back to a saner life, I guess.